Episode 10: Pigment Dispersion Techniques, Equipment and Stability in Automotive Coatings. In this episode, we explore pigment dispersion, one of the most critical steps in automotive coating formulation. Pigments, whether organic, inorganic, or effect-based, must be uniformly distributed in the binder system to achieve optimal color, opacity, gloss, and long-term stability. Poor dispersion can lead to defects such as streaking, haze, flocculation, inconsistent color, settling, and reduced durability. Understanding the techniques, equipment, and parameters that control dispersion is essential for high-performance automotive coatings. Pigments naturally exist as aggregates or agglomerates. Primary particles, especially in titanium dioxide or carbon black, are extremely small and prone to forming larger clusters due to van der Waals forces, hydrogen bonding, and electrostatic interactions. Agglomerates act optically like larger particles, reducing hiding power, color strength, and gloss. Therefore, the goal of dispersion is to break down these agglomerates into primary particles or stable secondary aggregates, and to wet them completely with the binder. Dispersion involves both mechanical and chemical considerations. Mechanically, high shear forces are applied to the pigment binder mixture using mills, dispersers, or specialized equipment. Common equipment includes bead mills, ball mills, sand mills, high-speed dispersers, and ultrasonication systems. The choice of equipment depends on the pigment type, particle hardness, particle size, and required dispersion quality. For example, hard inorganic pigments like rutyl TiO2 require more energy to break down agglomerates than soft organic pigments. Particle size reduction during dispersion increases surface area, which improves pigment, binder interaction, color strength, and hiding. However, excessive mechanical energy can damage sensitive pigments, especially affect pigments and pearlescent flakes. Flake breakage reduces optical performance, diminishes color travel, and can cause inconsistent visual effects. Therefore, process parameters such as speed, time, temperature, and media size must be carefully controlled to balance dispersion efficiency with pigment integrity. Chemically, dispersion is aided by wetting agents, surfactants, and dispersants. These molecules adsorb onto pigment surfaces, reducing surface tension, preventing flocculation, and stabilizing the particles in the liquid medium. Dispersants are particularly critical for high surface area pigments like carbon black, organic pigments, and fine titanium dioxide. They create a steric or electrostatic barrier that keeps particles separated and ensures long-term stability in storage and after application. Rheology is also impacted by dispersion. A well-dispersed pigment system exhibits predictable viscosity, flow, and leveling properties. Poorly dispersed pigments can lead to viscosity spikes, shear thinning or shear thickening behavior, and uneven film thickness during application. High-quality dispersion ensures consistent spraying, brushing, or rolling behavior, reducing defects such as sagging, orange peel, or uneven coverage. Stability over time is another critical consideration. Pigments tend to re-agglomerate if surface forces overcome dispersant action, or if environmental conditions change. Formulators monitor zeta potential, particle size distribution, and rheological parameters to ensure that dispersions remain stable during storage, transport, and use. The binder system, solvent composition, and temperature also influence dispersion stability. Effect pigments and pearlescent pigments require special attention. Because their optical performance depends on particle orientation and integrity, excessive milling can reduce flake size, create fines, and degrade metallic or pearlescent effects. Low shear dispersion techniques combined with optimized surfactants are often used to maintain flake morphology while achieving adequate wetting and distribution. In multi-pigment systems, interaction between pigments must also be considered. Agglomeration of one pigment can induce flocculation of others. For example, carbon black may interact with titanium dioxide if dispersants are insufficient or if surface charges are mismatched. Careful selection of dispersants and sequencing of pigment addition is required to avoid instability, color shift, or haze. Temperature control is essential during dispersion. Excessive heat can degrade organic pigments, alter binder viscosity, or reduce dispersant effectiveness. Controlled cooling or staged dispersion processes are often employed in automotive coatings to maintain pigment and binder integrity. In addition to mechanical and chemical strategies, Monitoring dispersion quality is critical. Particle size analysis, sedimentation tests, color measurements, and viscosity profiling are used to ensure reproducibility and performance. In OEM automotive coatings, strict specifications for color, opacity, and stability make dispersion control a high-precision process. In summary, pigment dispersion is a cornerstone of automotive coating performance. It combines mechanical energy, chemical stabilization, and process control to ensure that pigments are fully wetted, evenly distributed, and stable. Proper dispersion maximizes color strength, hiding power, gloss, and durability while preventing defects and ensuring consistent application. Mastery of dispersion techniques is essential for producing high-quality, reliable automotive coatings that meet demanding OEM standards. If you have any doubts about pigment dispersion techniques, equipment, or stability in automotive coatings, leave your questions in the comments and I will clarify them.